Sorry, Priyanshu. Priyanshu, so why don't you be up?
Good afternoon, everyone. So, myself, Priyanshu, I have been working in the formal verification industry since past 5 years. I started my career with OSCE technology, and from last 2 years, I have been leading the formal efforts at Qualcomm. So that's about myself. So the topic for today's talk is going to be the recipe for the strip tape out of derivative SoCs, how we can use formal based SEQ and connectivity checking to left shift the verification of the derivative SoCs. So the agenda of the today's talk is going to be the problem statement. What's the problem statement? Then what is the proposed methodology, how we are leveraging SEQ and reverse connectivity to tackle the various problems that we face in verification. Then we are going to talk about the challenges which we have faced and how we went about resolving them. And then finally we'll talk about the results. So the problem statement is very simple. What we are addressing is simply that we cannot lose out our customer due to chip tape out delays. Lately, we have seen that PPA demands are impacting chip tape outs. And these supply demand challenges often lead to fab migration. In these kind of projects, we mainly have, majority of the cores we have reused with minimal changes such as tech node, then ECOs if there are any bug fixes, and then addition of latency, meta stability, and clock gating. So majority of the functionality of the cores are intact with these basic changes. Now to verify these projects, a lot of man months and project time is required. We have to redo whole regression and coverage analysis. But the thing which we are missing with that approach is we are not reusing our existing verification. So how can we use formal verification to use our existing verification environment and left shift the entire verification? So that is what we are going to talk about. So this is the methodology which we are proposing. So I hope the font size is visible, but I'll talk about it. So to verify any SOC, what do we have? We have a lot of cores like CPU, GPU, debugger, and many more cores. Now, in a take porting based project, most of these cores are being reused with very minimal changes. So what we can do is we can apply sequential equivalence checking between the parent chip and the derivative chips for these cores, and we can achieve sign off on those cores using SEQ. So that is being covered by design verification. Then we should also verify the integration aspects. So basically when these cores are going into the SoCs, they should be connected properly inside. They should be connected properly. They should talk with each other properly. So we are leveraging formal based connectivity to verify the integration aspect. Now I'll walk you through the flow. Let me see if I can, yeah. So first we'll start with verifying these cores. So let's say in your SOC there are 20 cores, and out of those 20 cores, 15 cores have not gone through any change. Then we can run each one of those cores one by one through these flow. So first we'll start verifying the core. We'll run SEQ. I hope everyone is familiar with SEQ. Yesterday we had a talk from Cadence on C versus RTL. So over here we are doing RTL versus RTL check. So what we are doing is we are running SEQ and between the parent and the derivative design, and we are checking if the properties are converging or not. If they are converging, then we are good. We just need to analyze the results if there are any failures or not. If there are no failures, then we are already done. The core has been verified. If there are any failures, then we need to see whether these failures are due to the intended functional changes or not. If they are unintended changes, then congratulations, you have found the RTL bug. You need to fix the RTL and then validate the RTL to finish the sign-off process. Otherwise, you will have to, basically otherwise you would have isolated the area of change, and then you can assign it to the DV resources to basically write some directed test cases to verify these changes. Now, if in the first step, if the properties had not converged, then what we can do? We can use divide and conquer technology, and we are basically referring it as hierarchical SEQ. So I'll take a deep dive into hierarchical SEQ in the coming slide, but now let's move on to the integration aspect. So how we can verify integration aspect? So again, to verify the integration aspect, we are using the connectivity app. With the proposed flow, we have been able to identify RTL bug in the derivative SoC. We have been able to identify the addition of the connections in the derivative SoC, deletion of the connections from the parent SoC, changes in connections, and if there have been some name changes, then those kind of aliasing errors we have been able to find. So, although there are lot of, there are lot of categories of issues which we have found using this. Few of them were RTL bug. The other issues are also very useful because we can share them with the DV teams, and they can then intelligently use these results to craft their regressions for better performance. So the idea with this methodology, the entire flow, is to enable DV team to align more resources and more time towards the specific things which have gone major changes. So moving on, now I'll take a deep dive into hierarchical SEQ, and then we'll talk about reverse connectivity. So this is the flow diagram for hierarchical sequential equivalence checking. So we feed the parent and variant chip database into the formal tool, and we then partition the cores on the basis of complexity. Initially, you can partition them on the basis of, basically, if you know that some cores have not gone through any changes, you can simply take the entire core as your DUT top, and you can run SEQ over there. Now, while running the SEQ, it might happen that your properties are not converging on that core. So what you need to do next is you need to identify the complex elements inside that core. These complex elements could be memories, FIFOs, any sub-module like complex FSM, anything. Anything can lead to complexity. So one of the way to identify complex element is to dump the design statistics using formal tools. Now, once you have identified the complex subunits inside a core, you can create and run equivalence model against the parent and variant chip database for these cores. Now, once you have verified these cores, you have verified these complex elements, you can black box them while doing the verification of the core top. That way, you will not run into the complexity problem. And even if you are running into the complexity problem, you need to further break it down. For example, let's say we identified a complex FSM over here, right? And we did SEQ between parent and child. Still the properties are not converging. We can go one level down again and do the whole thing again. Now once you do this, and if there are no failures at all, then we can simply black box this while doing the hierarchical SEQ at the core top, and we can run the equivalence at the top level with the complex element being black boxed. This technique is often known as assume guarantee in formal, wherein you assume something to be true and then prove the problem at the higher level. Now, if there are any failures while doing the SEQ at the core top level, We need to analyze them. These could be bugs or these could be intentional changes as well. So not only this flow is capable of identifying bugs, but it is also capable of identifying the areas of the design which has undergone some intentional changes and where we need to put in more effort. So moving on. So the last slide we were focusing on verifying the design. Now this flow is, with this flow we are targeting the verification of the integration aspects. So whenever we have multiple cores interacting with each other in the SoC, we need to make sure that the pins are properly connected. To do that, we have introduced the reverse connectivity flow. As the name suggests, we have exploited the formal tool to do a reverse engineering over here. So what we are doing is simply nothing. So we have a parent chip and a child chip. Parent chip is A, child is B. So we extract all the connections from chip A. So you can simply run a script, pass your script and design. A script is nothing but a set of tickle command. You can pass them through formal tool. And then formal tool will generate a list of CSV which will be having source and destination. Basically the connectivity spec. You can treat that spec as the golden specification, and then you can load that specification into the derivatives chip. And once it is loaded into the derivative chip, you can run all the properties and analyze the results. Now, there are three categories of the failures. We would have pass, some fails, and then there would be parsing errors. So if for pass we don't have to do anything. If there are failures, we need to analyze the failures. There could be a real RTL issue, or there could be an intended change in the chip B. For parsing errors, it could be due to the fact that the connection have been removed and no longer needed in the derivative chip, or simply the name of the signals have been changed in the derivative chip. So we'll run into these parsing errors. So this is one side of the story where we have taken the spec from chip A and we have run it on chip B and identified some issues. Now we also need to do the opposite thing where we'll get the specification from the derivative chip, loaded into the parent chip, and through this we can find what all connections have been added into the parent chip. So again we will run into some parsing errors. There will be some name aliasing issues and some additions. So all these additions, connection removals, name change list, these can be shared with the DV team, and they can intelligently craft their regressions, and they can basically align their resources where they want to spend more time and what should be the area of focus for them. So now I'm going to be talking about the challenges that we have faced with equivalence checking and reverse connectivity. So let's start with equivalence checking. So due to tech node changes in the parent and child, the memory models, reg array and other library cells had changed. So when we started applying some black boxes, the tool was not automatically able to map the signals. So when we do SEQ and when we do black boxing on the internal blocks, what happens is formal tool automatically applies assertions on the input of those modules and assumptions on the output of those modules. This is needed to make sure that the end-to-end flow of data is intact, right? So and these assertions and assumptions are automatically applied. And so over here, the tool was not able to automatically map these signals because of the change in name and hierarchy. So we had to manually map those signals. So little bit of manual effort was required over here. Then our designs had some combinational loops, and formal tool doesn't really like combinational loops. So we adopted various loop handling strategies provided by vendors. Then most of our combinational loops were resolved by these strategies, but still we had to, for some of the loops, we had to apply cut points and add some assumptions to remove or rather break those combinational loops. Then convergence is always the problem with formal. So if your RTL and spec, if your spec and implementation are very far away, meaning their implementation is not exactly similar, then you'll run into convergence issues. So again, as I talked in the previous slide, the hierarchical SEQ was adopted. We used black boxing techniques and assume guarantee to tackle these challenges. Then another issue was with the meta stability in CDC cell. So in the derivative SoCs, we see that there have been introduction of meta stability in CDC cell. So it was leading to some false failures. So we had added some over constraints to disable these meta stability issues, basically to disable the meta stability feature and overcome those false failure. Then last but not the least, one very special kind of failure was there. So when we apply black box while doing the SEQ, the assertions would be written on the inputs of those modules, right? But if those input signals have been left undriven from one level up in the hierarchy, then formal will drive random value over there and you will run into false failure. So we had manually disabled those assertions. Now coming on to the challenges which we faced in reverse connectivity. So we had seen that there was some path delay being introduced in the derivative chip between source and destination. So to overcome this, so there are multiple ways to overcome this, but the simplest is to basically pass any large delay value in the connection so that tool will not show it as structurally disconnected. Then we had also seen a large number of parsing error due to the changes in the name of the signals. So this was resolved by doing some intelligent, basically incorporating some intelligence in the scripting to map the signal name using some regular expressions and things like that. Then while black boxing, so we were doing this reverse connectivity at the chip core top, and it was taking a lot of time for the tool to load the design and create the formal model. So we had black box lower level module, but this was leading to some false failures in the connectivity check. So to trim this false failure, we run parent versus parent and child versus child connectivity. And then we had gotten a list of the failures which we used to mask those false failures. Now coming on to the results. So we deployed this methodology on 13 cores in one of our derivative chips where the design had not gone through any functional change. So this chart over here represents the runtime. So this simulation runtime was from the parent chip and this formal runtime is from the derivative chip. So across all core, we can see that there have been approximately 60% reduction in the runtime. Overall, we have been able to save 6 man-month of effort and 60% overall left shift was observed in the DV cycle of the entire SoC. Yeah. Now coming on to the conclusions. So advantages are, we have seen the improved efficiency, we have saved a lot of time, we didn't have to run the regressions again and again, we didn't have to do any coverage. Just by using SEQ, we signed off multiple cores in our derivative SoC. Then we have seen improvements in the quality as well. With this flow, we have been able to detect the issues which were left uncovered by simulation. Then we have been able to detect unintended changes between parent and child. Now, finally, I have summarized the list of bugs which we have been able to find with this flow. So with equivalence checking, we have been able to find if there is any structural gap between parent and child design, if there are any POR value mismatches for the register, hardware version changes in register, any unexpected functional change around a signal, we have been able to catch it with SEQ. Any changes in the design parameter which is impacting the overall functionality, we have also been able to catch those kind of issue. Any unwanted delay introduction in the data or control path of the signal. So these are the categories of the issues which we have been able to find using SEQ. With reverse connectivity, we have been able to detect the connection bug in the derivative chip. Apart from that, we have been able to identify the specification issues, and this can prevent bug escapes later in the verification cycle. We have been able to identify the removal and addition of the connections and the signal name changes. So this is the categories of the issues which we have found using equivalence checking and reverse connectivity. Yeah, that's it. So I'm open for questions now. Yes, please, Kiran.
Hello. Hey, good work, buddy. Anything that the formal can actually ease the design thing is very good. So I had a couple of questions. So when you talk about the hierarchical SEQ, right? How much automation went into it, and are you trying to push that to the tool itself? Because most of these automation should be done by the tool itself.
Yeah, so like we are in constant touch with the vendors. Like as I talked about some of the issues where we had seen the changes in the library cells when we migrated from one foundry to another. When we black box those modules, the tool was not able to automatically map those signals, right? So there we had to automatically apply the black boxing.
I think all of us together should push. Where is Girish? Right, so,
Today.
yeah.
I'm track chair today.
Complexity kind of report where the tool himself can say that if these are the number of flops, this is how you have to partition, because I've seen that often junior engineers, if they are running SEQ, sometimes they don't know whether it's because of complexity, they have to break the design and all that, right? So if it comes from the tool saying that, hey, these many number of flops, after that we are pushing that.
Thanks, Sandeep.
Second question is with respect to your reverse connectivity. I mean, 6-man-month efforts looks too too unrealistic to me. Okay. Second thing is, suppose let's say if we are looking at it, what kind of coverage metric did you have to sign off on that? Because the idea is good, getting from A to B versus again B to A, the reverse connectivity on both, and then checking again reverse connectivity. If the based on the tool also has a lot of limitations, which you touched upon some of them. But then when the sequential depth actually grows more, you do have limitations there, right? So having said this, did you sign off using any coverage, any toggle coverage or any sort of metric to sign off on those?
Yeah, toggle coverage was being run.
What are the numbers?
Sorry?
What are the numbers?
I don't have the data on the numbers. Actually, it was done by multiple
We'll take it
teams.
offline. We'll take it offline.
Yeah, if your SEC is proven, do you really need reverse connectivity checks?
I didn't get you.
If your SEC is proven, do you really need reverse connectivity?
Yeah, because with SEC we are only verifying the design, right? Now there are, let's say, 10 design IPs and they are sitting inside the SoC and they are talking to each other. If those connections are not good, then the overall functionality of the SoC would break. So you also need to make sure that the connections are proper.
SEC says that the
No, so-
designs are equivalent.
So the other way to answer your question is to run SEC at the entire SoC level. If you have run the SEC at the entire SoC level, then you are good. Then you don't have to do anything. But otherwise, you will have to do the connectivity.
Thank you.
And by the way, the idea here is to, help the DV team to identify the critical areas where the design has gone changes and work closely with them to basically optimize the resources and timing. So we are not saying that this is the foolproof solution and if you have done this, then you are done and you don't have to do anything. Other things are definitely required.
Yeah, I have a question. Yeah. So the SoC must have had multiple clocks. So in the SEQ proof, did you consider different clock frequency combinations? Did you have a strategy for dealing with it?
Yeah, we did consider different clock strategies. So the flow which we had adopted was we initially gave the same frequencies, and when we have same frequencies between both, when we have same frequencies across the various clock domains, then the convergence is usually more, right? So we had adopted that strategy to go deeper into the design with the same clock frequency, but we had also run with the original frequencies which were there in the specification.
Okay. And one more question.
Yeah.
You mentioned that when a change is intended, like there's a difference between the two SoCs. You mentioned you isolate logic. So can you give an example of how logic is isolated?
By isolating, I mean we have isolated the areas of change, right? Where, so from parent to child, there has been some change, right? If there is a failure with SEQ, and it can exactly pinpoint to the root cause, right? When you will debug the waveform, you'll get to know which change in the design is leading to this failure. So by isolating, I mean identifying the piece of or the code in the RTL where they have made the change.
Is it like a constraint being added to prevent some feature getting exercised?
No constraints have been added. So that's the beauty with SEQ. You just need to make sure that both the signals in parent and child are driven same values, and you are done. You don't have to add any more constraints.
Okay. No, what I'm trying to ask is there are two designs, and one of them has an additional feature. So when you do the SEQ check, you are going to see failures whenever the feature is enabled or the new functionality gets exercised. So how exactly is that isolation is happening is what
I think you're talking about the chicken bit where we can use that bit to disable a particular feature and then we can do the equivalence between the two designs.
Was that the kind of isolation you were talking about?
No, that's not the isolation I'm talking about. I'm just talking about the intended functional changes and where they have been made in the design.
Okay, if you are doing a ECO in the design, then yeah, of course, that's where we call about the chicken bit, right? So you have to add a chicken bit, then the SEQ will work perfectly fine. Until we do not do that, then, it will show the differences, and based upon that, we have to come back again, what kind of isolation we have to make. But mostly in our cases, because it's a tech board, then we do chicken bit on the ECO so that we disable it and then we see that how it's proven. I mean, that's much easier to do that, by the way, for tech board.
Hi. In the connectivity checks during parsing, like for parsing errors, you mentioned that for the scripts we can do some intelligence. So I just want to know about that, like what intelligence, or because I was working on kind of the similar pattern for Cadence Jesper Gold tool and the connectivity checks basically. So I just wanted to know about like integral scripts or in scripts, how did you manage that thing? Because hierarchical name changes will be there.
So actually that depends upon how designers are, what kind of naming conventions have been used while coding this, while writing the name of the signals in the RTL. If there is no consistency between the naming of the signals across parent and child, then it becomes quite difficult to do that. But if there is some similarity, like if you can grab a particular characters from a string
yes.
between parent and child, and then you can map them across the two, then only you can enable some sort of intelligence in the script. Otherwise, it's not easy. It's not straightforward.
Oh, thank you.
Thanks, Priyanshu.
Thank you, Girish. Thank you, everyone.
Yeah, so Priyanshu, stay there for a second. May I request Vichal to hand over the certificate to Priyanshu?